We present MoSca, a modern and full-stack automatic 4D reconstruction system for monocular videos. This short video provides a brief introduction to our method and shows visual results. We study an extremely challenging task. Given an unposed in-the-wild monocular RGB video, we aim to reconstruct a render-able dynamic 4D scene that can be viewed from novel viewpoints at any time. To address such a challenging and ill-posed inverse problem, we utilize a novel motion scaffold, MoSca, representation as shown in the video. Specifically, MoSca is a sparse graph of SE3 motion trajectories, which compactly and smoothly encodes the underlying motion and can be interpolated into a dense SE3 deformation field. We will briefly introduce the method in the last part of this video, and now we first show visual results on diverse casual videos captured in the wild and then comparisons on DieCheck and NVIDIA benchmarks. We start with the 4D reconstruction from the Sora-generated videos. In the following, all the visualizations will be in the same format. The left top shows the input monocular video, the left middle is the visualization of the underlying MoSca, the left bottom is a zoomed-in novel view. On the right, we show zoomed-out global 3D views. The top left in the square shows the color rendering, and the top right shows the solved camera where the out-of-view area is red. The bottom left shows again the visualization of the underlying MoSca, and the bottom right shows the long-term trajectories of each Gaussian. Given the fact that MoSca is a fully automated system starting from a list of unposed images, the following real-world results are from extremely challenging setups and can be considered as highly non-trivial in the current literature. MoSca also works for vertical internet short videos. Now, we show results on robot videos from the internet. We now turn to movies and TV show clips. Here we show casual videos from Davis dataset. now show the comparison with state-of-the-art methods on the challenging iPhone die-check dataset. The white masks are the co-visibility masks proposed on die-check. We also show the zoom-out visualization of iPhone sequences. From the left are underlying MoSca, Gaussian trajectories, and color renderings. Finally, we show the comparison on the widely compared NVIDIA benchmark. Finally, we quickly introduce our method, and more details are in our technical paper. Given an input video, our system first leverages the prior from powerful 2D vision foundation models. Specifically, we infer the monocular metric depth, the long-term pixel tracks, and the epipolar errors induced from optical flows, which provide strong cues of the underlying geometry and motion of the scene. In the second stage of our system, the camera poses can be easily initialized via bundle adjustment based on the previously inferred tracking and depth. Now we can focus on solving the MoSca and dynamic components of the scene. We identify the foreground 2D long-term tracks from the previously inferred epipolar errors and lift them to 3D via the estimated monocular depth. However, all the rotation components and occluded translation components are unknown on the scaffold. We initialize these unknowns with lines and identity orientations and optimize the MoSca under several physics-inspired deformation regularizations. Please see section 3.2.3 for more details. The above optimized MoSca approximates the underlying deformation field, considered both deep-learned foundational priors as well as physical deformation constraints. Essentially, MoSca enables us to anchor Gaussians that are lifted and initialized from depth back projection across all different times, and then deform and fuse all Gaussians collected from different times to any desired target rendering time. Finally, the full dynamic scene representation can be optimized via Gaussian splatting. Please see our paper for detailed technical introduction. Thanks for watching, more details are in our paper.